In this video, I want to explain what a capacitor is. In a previous video, I used a water analogy to explain the concept of voltage, current, and resistance. And here I have a garden hose that's shown in green. I have a nozzle and I have a piston. And in this hose is filled with water, which is analogous to charge Q. And as I push this piston to the right, that's analogous to voltage that causes a current to flow out of this nozzle, and this nozzle causes a certain amount of resistance R to current flow. Now I can use a similar analogy to explain what a capacitor is. Let me erase this. Let's consider a tank that can hold water. And I'll draw a tank that can hold twice the amount of water to the right. Let's say I pour a gallon of water into the tank at the left and I almost fill it up. And we'll call this gallon of water. We'll represent that by charge Q. Let's say I pour the same gallon of water to the tank on the right, and it fills up this amount, and it has the same amount of water, or the same amount of charge in the analogy. The electrical symbol for this water tank is the capacitor symbol. At the right, I have still a capacitor. It's a bigger capacitor. The capacitor at the left, I could say it has a certain value. It has a certain capacity to store charge. I could call that capacity 1 farad. A farad is just a unit of capacitance. It says, what is the storage capability? Now look at this tank on the right. It has twice the storage capability. So in the capacitor analogy, this would be a 2 farad capacitor. I'll call F for farad. So in the tank at the left has a 1 farad capacity, which I'll draw this way. This has twice the capacity at 2 farads. So what is a capacitor? A capacitor is a device that stores charge. Just as this tank stores water, the capacitor stores charge. There's a simple equation that tells how much charge the capacitor stores. We say Q equals to the capacitance C times the voltage V. In our water analogy, the level of the tank is analogous to voltage. So at the tank at the left, I have a high voltage. Tank at the right, the voltage is only half as much. I'll call it 1/2 V, or V over 2. So if I write the equation for the charge on the capacitor at the left, I can say the charge, in this case I poured in a gallon, but let's say a gallon is equivalent to a coulomb of charge. I could say this capacitor is 1 coulomb is equal to the capacity, which is 1 farad, times the voltage, which is 1 volt, which is the height of the water in the analogy. The capacitor at the right, I could say, has the same charge, 1 coulomb equals 2 farads times 1/2 volt. So each capacitor stores 1 coulomb of charge, but the capacitor on the right has a greater capacity. And for the same amount of charge, you only get half the voltage. Let me erase this. Analogies are never perfect, and the water analogy for the capacitor is not perfect either. Let's consider that for a second. Here I have a tank that I used as an analogy to a capacitor, and I fill it with water. The capacitor actually works a little differently. If I have a capacitor and I put charge in the top, a charge Q, I develop a positive charge on the top plate and a negative charge on the bottom plate. And as charge flows into the top, this charge also flows in the bottom terminal. Same amount of charge flow. But when I put water into the tank, it just sits there, Q. It doesn't flow out. If it flowed out, I wouldn't have the charge in the tank anymore. So the analogy is not perfect. In the capacitor, I can have charge flow, or I can have a current flowing in this terminal and this terminal at the same time, and still have a charge on the capacitor. So the water analogy is not perfect, but it gives you at least some sort of idea to something that you're familiar with. Let's consider what a capacitor is physically. Let's say that I have a plate of metal. And below this plate, I have another plate that's identical in size. To this top plate, I connect a wire. And underneath to the bottom plate, I do the same. I connect a wire. And this is what a capacitor is physically. If I induce a current into this top terminal I get a current flowing out the bottom terminal that's the same I. So as this current flows into the top terminal, I get a positive charge on the top plate. And at the same time, I get a bottom plate charge that's negative. So think of it this way. As the top plate develops a positive charge, that repels positive charges from the negative plate, because like charges repel each other. So as a result, I get a current flow out the bottom plate. There's a equation for this capacitance, or for this capacitor. C equals epsilon times the area of the plate divided by the distance between the plates. So in this case, the distance between the plates is D, and the area of the plate is A. So what is this epsilon? This is the Greek letter. It's a symbol for permittivity. And permittivity is a physical characteristic of the region in between the plates. So the permittivity is associated with this region D in between the plates. And different substances have different permittivities. For example, mica might be used in between the plates, and glass might be used, and they're slightly different. As the area of the plates increase, the capacitance increases. As the distance D decreases, the capacitance also increases. So in a capacitor, you like to make D as small as possible to get the most amount of capacitance. But there can be a problem associated with that. Let's, for a minute, Let's move this out of the way. And let's consider the two plates. And we have a terminal and a terminal. And we send in a current I into the top plate. And that develops a charge on the top plate. And that repels positive charge on a negative plate. So we end up with minus charge on the negative plate. And the charge has been pushed away. So the same current that flows in the top plate flows out the bottom plate. But as the current flows in the capacitor, remember that the charge on the capacitor is the capacitance times the voltage. So let's solve this for voltage. Voltage equals charge divided by the capacitance. So as we add charge to the capacitor, as the charge increases, the voltage V increases also. So eventually, if we add enough charge to this capacitor, this region in between will experience a very large electric field. This is where the energy is stored, in this E field. And if the field becomes too strong, it can cause this material between the plates to break down. So all capacitors will have a breakdown voltage. If this this distance between the plates is small, it will break down more easily. If this distance is large, the breakdown voltage will be higher. In this video, I want to explain what a capacitor is. In a previous video, I used a water analogy to explain the concept of voltage, current, and resistance. And here I have a garden hose that's shown in green. I have a certain amount of resistance R to current flow. Now I can use a similar analogy to explain what a capacitor is. Let me erase this. Let's consider a tank that can hold water. And I'll draw a tank that has a nozzle, and I have a piston. And in this hose is filled with water, which is analogous to charge Q. And as I push this piston to the right, that's analogous to voltage that causes a current to flow out of this nozzle. And this nozzle can hold twice the amount of water to the right. Let's say I pour a gallon of water into the tank at the left, and I almost fill it up. And we'll call this gallon of water. We'll represent that by charge Q. Let's say I pour the same gallon of water to the tank on the right, and it fills up this amount. And it has the same amount of water, or the same amount of charge in the analogy. The electrical symbol for this